Dr. Jones is coming back to us now as Dr. Jones. Not to be confused. So you haven't rated any lost arts?
No, but I do have the hat.
Okay, you have the hat. All right.
We'll just call him Indy.
Yes, we'll call him Indy. Codename Indy. So Dr. Jones is joining us. He's going to talk about his work with the CHARA Telescope Array. He's going to talk about what the CHARA Telescope Array is. And we'll have approximately 45 minutes to an hour with a little bit of time afterwards for Q&A. And after that, we have our drawing. You do have to be present at the drawing to win, and you have to have your name badge to win as well. So that is the catch. We got some cool prizes. We have a 10-inch StarSense Dob. We have a bamboo 3D printer. We have a couple of telescopes from Celestron, Starfield, and Explore Scientific, and a radio control, I believe, helicopter, and a radio control car, and a few other accessories and whatnot. So with that, all yours.
All right, thank you very much. And thank you all for being here, and thank you for inviting me to come talk to you. I'll be telling you all about the CHARA Array and seeing the stars up close. So the CHARA Array is a 6-telescope interferometer on Mount Wilson, at Mount Wilson Observatory just outside Los Angeles. So here is a cartoon of the site with our 6 telescopes highlighted. The 100-inch telescope here is where Hubble did all of his work on, that made him Hubble. So it's a very historic site, very cool to go out there from time to time. Mic's not working? Is the mic? Yeah, I think the mic is for online. It's, yes. Right, so yeah, for an interferometer, basically we are combining the light from these 6 different telescopes, taking advantage of the wave-like property of light to combine them, the light from these telescopes, and get interference patterns, and measuring those interference patterns tells us stuff about what we're observing. So I'll get into more detail on that in a minute, but just broad strokes, we have extremely high resolution because the resolution of an interferometer is based on the separation between telescopes. It's not based on the size of the telescope itself. So with having a 331-meter baseline, we end up being able to resolve things as small as half a milliarc second in the near-infrared or 0.2 in the visible. So this is, at the moment, the best resolution of any optical telescope in the world. So it's cool to work there. More about the resolution. So here is an image of the Keck telescope, or one of the Keck telescopes. It's a 10-meter diameter telescope. And the resolution for a single dish telescope, a traditional telescope, is based on the wavelength and the diameter of the primary mirror. So for something like Keck, you can get down to 17 milliarc second resolution. Whereas with CHARA, because as I said, it's based on the wavelength and the baseline, the separation between telescopes, we end up getting down to 0.21 milliarc seconds. So it's really, the best that there is. So here we have a little video tour of the site. So we've got 6 telescopes in the array at the moment. Each telescope is a 1-meter telescope, and they each have adaptive optic systems on the side of the telescope that lets us freeze out some of the atmospheric component of the starlight. And we send the light from all of our telescopes through vacuum tubes, light pipes, into our central combining lab, which is in this room within or building within a building to help with thermal stability. Here are a lot of the computers that make it all work, right outside the central lab. And then inside the lab is where all of the magic really happens. So because the light all has to, and I'll actually pause it here. Because the light all has to go exactly the same distance through each telescope in order to get that interference, we have to have this 50-meter long hallway with mirrors on rails to be able to equalize the path length, because the light will hit one telescope before it hits another, and so we have to have on the back end a way of equalizing the distance that the light travels. And so we have these carts that have a precision. We need to know where those carts are exactly within like a few nanometers in order to make it work. And yeah, so here is, now it's going to show our actual beam combiners. So basically this is all the light from the 6 different telescopes gets combined through these optics pairwise. So you have telescope S1 and S2 because it's on the south, the 2 telescopes on the south wing, and then we've got the east and the W. So you combine like S1, S2, S1, E1, S1, E2, etc.
What type of focusing time or time differential do you need to be moving those mirrors?
Once we are actually on the target, the carts are moving. They're moving, well, for nanometer precision, they're moving pretty fast. So maybe it'll be a few meters over the course of 10 minutes, whatever that translates to in speed. But yeah, and so needing to maintain that precision the whole time. No, it's not. It's usually going to be a smooth motion. Yeah.
Do the adaptive optics affect the path length?
A little bit, but enough that it's small enough that we can compensate for it.
How does the light exit the vacuum tube? Is there some sort of optical quality window there or something?
I'm sure there is. I'm not one of the hardware guys, so yeah, I'm afraid I don't have the answer, but yeah. Yeah, so putting it all into context, especially CHARA's excellent resolution, so you've got a fruit fly here, 0.12 inches. We could resolve it 1,900 miles away, which is about the distance from Atlanta to Los Angeles. Or to put it in more human terms, if you have an astronaut about Neil Armstrong height, you could measure how tall they were 5 times the distance of the Earth and the Moon from each other, so about 1 million miles away. But you can only do that if they were bright enough, and if the astronaut is bright enough, they're having a very bad day. But something that is, bright enough for us to observe is something like the sun, stars like the sun. We can resolve them up to 144 light years away, which means that for sun-like stars, we can get basically the solar neighborhood. And then for larger stars, we can get farther away. Smaller stars, we're more limited, but yeah, can get the sun-like stars within the solar neighborhood. Measure their sizes. So the sort of science we do at CHARA falls under 3 main buckets. There's measuring the angular diameters of stars, and then if you have a distance to go along with that, like through the Gaia Space Telescope, then you can get an actual size for the star. And then we also do binary star orbits, measuring very precisely the separation between the binary companions over time. And then we also do imaging of stellar surfaces and the environments around stars. So for angular diameters and binary star orbits, we get amazing scientific results, useful across a wide range of stellar astronomy, and it's very complementary with the work of other observatories. Doing the high resolution side, doing the spectroscopic side, or what have you. But unfortunately, with these two buckets, there are no pretty pictures that come along, and obviously we astronomers all love our pretty pictures. So with our imaging work, we get those same great scientific results along with some pretty pictures. So I'm going to talk about a handful of these objects. The first one is a really obscure little star. I don't know if anybody here will even heard of it. Polaris. Yeah, so this one is the system I really like because it ticks all of the boxes and also happens to be the only star non-astronomers have ever heard of. And so it's very cool to have this system that we can talk about. So first of all, here is the Hubble Space Telescope image of the Polaris system. It's actually a triple star system. Here is A and B over here. I forget what their separation is, but large enough that we ignore B in our analysis because we're too close in. And then there's an inner companion here, Polaris AB, that Hubble is just able to resolve. And one of the other interesting things about the Polaris system, in fact this is for Polaris A, is that it's a Cepheid variable. So it's pulsing over time, and we can actually measure the size of the star over time and see that it does in fact change and see how it changes, which is, I think, very cool. With binary star orbits, this is just an example binary star, so this is an example of how binary stars might orbit each other. And then this is sort of the standard view that we use for like how we would publish a binary star orbit, where you're not measuring the orbits of the individual stars, you're measuring the relative separation of the stars as they go around each other. So it makes it easier to display, really. And so here is that diagram for the Polaris A-AB system. And this, I should also mention, this is all work done by Nancy Evans from Harvard. So we at CHARA offer about 100 nights a year through the NSF to the astronomical community. You apply through NSF, and Nancy Evans got some time to look at Polaris, and so this is one of our exciting partnership programs. So here is the orbit of Polaris A-AB, and so here are the points that Hubble was able to get down here, and then the CHARA points are here in green, and then this red point is a speckle interferometry observation. But we're the only ones who could have gotten this point right here, because that separation is just too small. And I think it was maybe one of these that is the image here. I think this separation that Hubble was just barely able to get is one of these. But then we can take it one farther and zoom in on the central star there and get an image of it. And we actually see that it's not just a smooth star. It's got these spots on it. And for Cepheids aren't really expected to have much spot activity, and so it's a bit of a mystery what exactly is causing the spots. And I will admit I'm not a Cepheid expert, so I don't know, but it's very interesting and requires more study. So this is moving on to another science case. This is one of my favorite recent images from the array. This is work done by Nora Ibrahim at University of Michigan. She's a grad student there. This is for a very, very young star, HD 190073. And it's about 30,000 years old. This is a class of stars called Herbig BE stars. So there's also the Herbig AE stars, which are very similar, just a little bit less massive. But this is a class of star that's very young, protostar, and very much in its planet-forming years. It's one of the classes of young stellar objects. Excuse me? Oh, okay. Right, so yeah, this system is about 6 times the mass of the sun, and it's 800 parsecs away and about 800 times the brightness of the sun. And so what we have here is we were able to actually resolve we weren't able to resolve the central star. So that's a point source here that has a little star symbol to make it visible. But then we were able to resolve the planet, the protoplanetary disk orbiting this star, and the sort of general emission from the system itself. And so, yeah, just for a scale, this line here is at the 3 milliarc seconds scale, and so that translates for that distance to it's about 2.5 AU wide. So one of the very cool things with this system is that NORA was able to get images in June and July, and over that month, she could see that this white blob feature here had moved. And that could just be, it's a warped bit of the disk, and the disk is rotating in such, well, so the disk it's consistent with disk rotation around the star. But what the blob itself is there's some speculation about it. There's multiple options, but one of my favorite options is it's a planet in formation. And that is a very real possibility here. So it's cool that we might be seeing planet formation in action. Another science case, sort of the things that we do at CHARA is RW Cepheus. It's a hypergiant star similar to Betelgeuse, but much bigger. It's about 13 to 32 million years old, which is very, very young as stars go, but also for a star with a mass of 25 to 40 times the mass of the sun. They die young, so it's near the end of its life. It's very evolved, even though it's very young, which is always weird to think about. But anyway, its distance is very unknown, or it's not well constrained. It's somewhere on the order of 3,000 to 7,000 parsecs away, and it's extremely bright. But yeah, so we're able to, my colleague who actually works at CHARA, Narcia Nugu, he was able to get this image in December of 2022. Yes, and so it's about 2.5 milliarc seconds wide, which for this distance, or rather for the range of distances that this star is somewhere on the order of 8 to 16 AU, which means that this star is about as large as the orbit of Jupiter. So, big guy. One of the cool things about this star is very similar to Betelgeuse. It has it's very, very variable. So this is here showing the magnitude in the V band over time, going back to 1900. So these gray points are from the digitized Harvard photographic plates. And then the black points here from about 1950 onward are from the AAVSO. So this has a very long baseline of observation on this star, and it periodically has these huge dimming events. But in the winter of 2022-2023, there was the biggest dimming event that had been recorded, also known as a great dimming event, similar to what happened to Betelgeuse back in 2020, where its flux went pretty suddenly, shot down. So it's a very analogous event. Oh, and this plot here is showing the same thing, except for taking all of the dimming events and plotting them on top of each other. So you can see that the 2023 one is the deepest dimming event that has been recorded. So NARCI was able to get images at various points along the 2022-2023 dimming event. So I was able to get it right at the bottom in December of 22, and then as it was re-brightening a few times in 23. And so you can see, so with images at CHARA, there's always some artifacts because we're not just a huge telescope. We're, several telescopes spread out. And so there's some artifacts, but you can and this is also at the edge of our imaging capabilities. But you can see roughly that these stars during the rebrightening phase, or these images during the rebrightening phase, are different than the image here in the dimming, at the bottom of the dimming. So the dark spot there's a dark spot here in the one at the bottom of the dimming phase, and then there's sort of a dark spot in the same place with bright features in the same place for the rebrightening phase. So the interpretation here is it's analogous to what happened with Betelgeuse, which is, or at least the best understanding of that situation is, these stars, these hypergiant stars, have convection going on and large temperature differentials along the surface of the star, and they're also throwing off gas clouds all the time. And so the thinking is that there was a particularly cool spot on the star itself, on the photosphere of the star, that then made the gas that happened to be at exactly the right temperature that if it cooled down a little bit, it would coalesce into dust and go from being transparent to opaque. And then suddenly you have this opaque cloud in front of your star forming, and from our line of sight. And so all of those things end up adding up to a huge dip in the brightness of the star. And so the fact that you have a very dark patch here, and it's also the scaling here is the brightest feature on here is not comparable to the brightest feature on here. They're all relatively scaled within the individual image. So the fact that you see this huge dark spot here and that it looks different, it all fits with that explanation. Yeah, and so there's some upcoming science that I'm really excited for, and I'm hoping we'll be able to see. So there is a recurring nova called T Corona Borealis, or T Corbor, that was seen in 1946, 1866, probably seen in 1787, and maybe seen in 1217, which that one is my favorite observation because it's some monk wrote in his journal that he saw a new star in Corona Borealis. But yeah, so this nova happens every about 80 years where the star brightens up to a second magnitude star. And it's been 79 years since the last outburst. So what the actual underlying system for this sort of nova is a white dwarf orbiting around a red giant star, and the red giant, and they're close enough, and the red giant is, as it ages, it's getting bigger, and so material is coming off of the red giant and going on to the white dwarf, and as that material collects, it eventually hits a point where it is hot enough and dense enough that it becomes a thermonuclear explosion and gets extraordinarily bright. And so it accumulates that much material to hit that critical point every about 80 years. So there's some speculation in the literature that perhaps it's not just 80 years that's the important part, but also where the white dwarf is specifically in its orbit around the red giant. And so maybe it's an integer number of orbits that it has to take before it goes off. Yeah, so if that is the case, then they predicted a handful of possible dates for the explosion. Obviously, March 27th, 2025 has gone. November 10th is the next possible date, which I'm really hoping it isn't that one because it's behind the sun. And so I'm really, really hoping that it's this June 25th.
So if it happens November 10th, will there be enough left over by the time it comes out of the sun?
Yeah, so it lasts, I don't know enough about Novi to be able to say this definitively, but I think we would be able to see the effects. I don't know if CHARA will be able to get any good images of it at that point. We might be able to see the afterglow, but it might be too big for us at that point. But yeah, because I think it becomes visible for us in like January or February. I might be remembering that wrong, but yeah. I'm really hoping for June because that will be when it's the easiest for us to observe and the best weather, because if it's this February one, February on Mount Wilson is terrible. So I'm really hoping for June 25th. But yeah, looking back about a decade ago, there was another nova that went off. It was about 3 times farther away than T Corona Borealis, and our technology was 10 years older. But we were still able to get the size of the explosion over about 40 days. And we were able to get some images. This was relatively early on in our imaging capabilities, but we were able to get some early images of the star when it was still, when it was at its, of the nova when it was at its brightest. And so, yeah, with this situation, yeah, we could see it sort of grows, and then the sort of brightest component of the nova, because it ended up being a multi-component, complicated structure of the explosion, the larger part became the dominant, brighter component after dust formed at the about 30-day mark. So yeah, that's the sort of a rough overview of the science we do, both recent science and upcoming science. And so now I'm going to talk about CHARA itself and what we're hoping to do with the array in the near and far future. So currently going on, we have a 7th telescope that we're adding to the system. It is movable. Right now we have different stations set up. So there are 2 stations that we have constructed and some plans for others, but can move it between this station here, which would give us a very short baseline, which means that we could, which means that Betelgeuse would not be too big for us anymore, because at the moment Betelgeuse is too big for us to resolve. We zoom in too far. Yeah. Yeah, so getting this really short baseline would let us get the broad features of Betelgeuse so we can actually get proper images of it. And then we also have a station out here that would expand our longest baseline to, I want to say 400 something meters. And the other key innovation with this is that we're not using the light pipes for this, this telescope. We are using fiber optic cables. And in fact, in order to make that work, we have to connect all of our telescopes to the lab with fibers. So here we have some fun pictures of the arrival of the telescope. So here is just the dome. The telescope wasn't installed yet, but this is showing off how we move it around the site with a little tractor there. And so driving around, and then this was the day the telescope got installed. And that night, after they installed it in the morning, they were able to get images with it. Got a nice image of the Whirlpool galaxy there. So yeah, this is a plane wave, just off the shelf, 1 meter telescope, which is pretty cool. Yeah, so as I said, the fiber optics are really the key thing with this, and really making sure we get that right and get that working will enable our future goals, our sort of medium-term future goals of really expanding the array out into what we call the CHARA Michelson array. So this is our sort of big vision for the future, where we've got our original baselines here, and then with this we would also, increase the size of increase the size of our telescopes and add more telescopes across the Mount Wilson site, and that is only possible with fibers. Yeah.
So when you expand it like this,
Mm-hmm.
are you going to have to expand the 50-meter building with the sliding?
Mm-hmm. We would. So one of the discussions with that is, at the moment, we send the light down, it bounces off once and comes back. So we could introduce a system where it goes back multiple times, and then we wouldn't have to expand the actual building, or we could expand the building out. So yeah, those are things that we are having to consider.
But you're running around all the scopes and will be going through fiber at that point.
Mm-hmm.
Can you just do a loop of fiber and get them all approximately the same and fine tune in the building?
Yeah, so that is what you would have to do for the large scale distances, but it all has to go exactly the same distance. So if you're hitting a telescope over here, you're going to be hitting, if the light's coming from this way, it's going to hit this one well before it hits that one. And so you have to, but also as the star moves over the night, that is going to change dramatically. And so you need to, compensate in real time. And so got to use the cards for that. And the shorter the cart is relative to the separations means a smaller window where you can observe the star. So you can do the large scale corrections with a fiber, but you really do need a significant amount of movability. So having telescopes spread out all like this is only possible with the fiber connection, because the Forest Service isn't going to let us build a huge pipe all the way out there. So.
Do you have to use any kind of amplification over those distances through the fiber optic, or is it that efficient that you don't need that?
So that's part of the tests that we're doing with the current the fiber connection on the shorter scale. So that's what, So I don't know enough about that to be able to say with much confidence, but I think that's part of, like, how good is the throughput? Can we actually do this? And could we go out farther?
I think you kind of answered my question. I was thinking, with that length of fiber, do you have to worry about the consistency of the cable itself?
Yeah, and so so one of the tests that they have done is they dug the trenches to put the fiber in and put temperature sensors all along it to make sure it's sort of the same temperature all along the fiber, and that is at least shown positive, like that it's all really relatively consistent temperature, and when it's buried, so that seems to be fine. But yeah, the polarization is the biggest concern at the moment. Maintaining a consistent polarization along the fiber is the hurdle, because the current stage of this project is they're able to get light from the telescope into the lab. They're able to measure the light, but they have not yet been able to actually find the interference fringes. And so I think they're close. So it's exciting, but just one last slide, and then I'm happy to answer more questions. So the very far future of CHARA is eliminating the need for physically connecting the light at all. And so we've started working with a group from Brookhaven National Labs, and they were actually out just a few nights ago, in fact. And the idea is, and this is beyond my level of expertise, but the idea is that you would be able to self-interfere the light at the telescope. And so if you do that and then combine the sort of self-interference patterns later on in the computer, then you can get the data that way. And so I know that they are able to do self-interference in the lab with laser light. So it's all about the technology development now to get it to real starlight. So it's exciting. The idea that we could maybe one day have, similar to how the folks in the radio do it, have telescopes spread all over the world. Yeah, and so I'm happy to answer questions now while we replay the video. Thank you.
Sorry,
Yeah.
just to clarify now, there were some pretty scary forest fires a few years
Yeah.
ago. You guys dodged the bullet, right?
We did. In fact, since I started at Georgia State in 2009, we have dodged 3 bullets. Yeah, in 2009, I think it was the fires came in from this way and cleared out a lot of stuff, and the firefighters really like us because is it right there? Somewhere in this area, it might be one of these. There's a 500,000 gallon water tank on the mountain that we keep. And so the firefighters really like us up there. But they were able to protect the site from fires from this way, and then fires from this way in 2020, and then fires that got up to here just at the beginning of the year.
So is the water there for fire suppression? Is that why it's there?
Yeah,
Oh, okay.
yeah. I mean, we also use it for,
Yeah.
regular stuff, but it's, yeah.
Okay, interesting.
So how much does the capability of one single telescope, how does that play into the larger
Mm.
the larger capabilities of the interferometry array? Like what you said you're using 1 meter plane wave
Mhm.
telescopes. Like how would your capabilities change if you had a 1/2 meter or a 2 meter one?
Yeah, so it gets complicated. Ideally, you want all of the telescopes to be similar.
Right.
But you are able to, because there's also, all of our current telescopes are not exactly the same. There's differences in when the last ones were recoded versus when the last differences in when they were recoded. And so there's differences in throughput for all of them. And so we are able to calculate that out. Ideally, you want them all to be the same, but you can account for some variation. I don't know if that answers your question.
I was just wondering if all of them were larger or smaller, how would that affect the final output when you combine them all together?
Yeah, oh, okay. So if they're all larger, like if you just doubled if you had 2 meter telescopes instead of 1 meter telescopes, that would let you go fainter. Because one of the quirks with this method is, right, we have to do all of this, path equalization so that you get the interference pattern. It all has to go the exactly same distance. But it also, if you try, because the atmosphere is moving quite quickly, you have to take very short exposures in order to maintain that fringe packet, and that's on the order of like 10 milliseconds. It's very short exposure, so we're very limited to bright objects. That's sort of our key limitation. We can get down to like 1/8 magnitude. But larger telescopes would mean we could see fainter objects. Yeah.
You're probably aware that we have a comet in the solar system at the moment that
Mm.
someone speculated is an alien spaceship.
Sure.
They've also speculated that right now it's going behind the sun and doing something nefarious over there. And they say, well, it's doing it because we can't see it from the Earth, but we have solar observing satellites in
Mhm.
orbit that do see it. And I'm just wondering if their range of vision, because they block the sun while
Mm.
they're observing things close to it, if one of those satellites would be able to track the possible nova.
Yeah, so, and also, James Webb is out at one of the Lagrange points as well, so it's not going to be as limited as we are. So I think there will be, well, no, I'm not going to be that confident. There will likely be data on the nova, even if it happens in November. It's just none of it will be coming from CHARA.
Could you use any of the Mars observer landers?
I mean, if it happens, then I'm sure that will be tried, because if you can't do it from Earth, yeah,
We have backups.
yeah, yeah.
Well, you're talking about, I think you said Betelgeuse is too big.
Mm-hmm.
What about Antares? How does it, have you done any?
Oh, I forget how big it is. I have access to the database because that's, you know, a big part of my job. So I'm happy to look that up in a minute. But yeah, I don't know how big it is off the top of my head. Yeah, sorry.
That's okay.
Yeah.
Talking about giant stars and everything, being able to image those, what about some of the dwarf stars in our neighborhood?
Yeah. We've got images for a lot of those, and even more. We've got, because the imaging capabilities for CHARA has really only been in the last decade or so, but we've been operating for 20 years at this point. And most of our work is the angular diameters. So yeah, I had talked about these buckets. So a lot of angular diameter work has been done on nearby stars.
I noticed on the slide about the great dimming,
Mm-hmm.
the rebound also went higher than any of the previous.
Yeah,
So is there any significance to that?
probably. I don't know. I'm sorry. I don't. Yeah, I study rapidly rotating A-type stars
Yeah, and I'm
when
also
I have time.
curious, when it dims, is that just, I'm sure there's still a lot of speculation about what's causing the dimming, but is, because you mentioned dust clouds,
Mhm.
formation of dust clouds maybe being a contributing factor,
Mm-hmm.
but when it dims, is it solely because of dust clouds, or does the temperature change? Is there something, I mean, does the frequency of the emission, does it get less red and go more towards?
Yeah, so my understanding of it is that there is sort of a temperature change, a slight temperature change, but that the gas cloud was at the right temperature, that the decrease in light to the gas cloud makes it then cool down and condense into dust. And so there is a temperature effect there on the actual star that then affects the environment that causes the huge dimming. So there is some dimming from the temperature of that localized part of the star cooling down. So there's some effect there, but then the much larger effect comes from the dust cloud. That's my understanding of what the consensus is on this. I don't know how, because this is not my focus, I don't know how sort of strong that consensus
I
is.
mean,
But
looking at that, there seem to be several cycles in play
Mhm,
here.
mhm.
Because if you look at 1950, then right before 88, and then 2023, those are larger scale dimmings and rebrightenings
Mhm.
compared to the ones in between.
Yeah.
So I'm just, I mean, is that something that you studied or heard being studied?
I'm sure it is something that people have studied. I don't know the results of that.
Assuming that our measurements are accurate.
Right.
Next
We
then.
don't have the error bars on them.
Yeah, no. Yeah. Any other questions?